Okay, so we're in section 8.6, and I guess in a sense we can say we've reached the promised land. That's a saying. I mean, basically what I mean is you've been learning in chapter 8 all these different rules about series. You're looking at these different series and do they converge or diverge, and you know, you have all this interesting information that you've learned regarding series. And in section 8.5, you learned about power series. Now we're looking at series where we involve a variable in the series, okay? And the question is, you know, why? Why are we learning all this? Well, the reason why is because we are able to take functions and actually represent them as power series. And when we're able to do that, it's very helpful because power series can be differentiated and integrated very easily, because power series is really just it's a set of terms based on like a polynomial, right? So what they do here is they start off, well, they have, I mean, here I can highlight this. I think this is important to mention. So in this section, we learn how to represent, section 8.6, we learn how to represent certain types of functions as sums of power series by manipulating a geometric series or by differentiating or integrating such a series. You might wonder why we would ever want to express a known function as a sum of infinitely many terms. The strategy is useful for integrating functions that don't have elementary antiderivatives, for solving differential equations. You'll see that in Math 282, where you can use power series to help you solve differential equations. And then also, you can approximate functions with polynomials, actually. That's another thing based off of a power series. Scientists do this to simplify the expressions they deal with. Computer scientists do this to represent functions in calculators and computers, like your TI-83 or 84, for instance. So this is real stuff here. This is real important stuff, and this is actually the material you're going to learn here in the next couple weeks. Here is actually probably some of the most important math material that you'll encounter in your math careers. You'll see this in higher level math, for instance, and you'll see it in other courses as well. And what they do here is they start off with a function, a rational function, 1 over 1 minus x. And they're saying 1 over 1 minus x can be represented as that power series. Okay, they're saying 1 over 1 minus x can be represented as the power series, where the terms are 1 plus x squared plus x cubed, and so forth. Okay, that's kind of interesting. That's kind of interesting. So, you know, how do they do that? How do they do that? Well, all right, I'll show you how they come up with this this power series. Okay. So, oh, by the way, well, before I go there, let me mention a few more things. So, you know, this is your first function. The function is 1 over 1 minus x. It's your first function where, hey, I could write this function as this power series. Now, by the way, what's that 1 plus x squared plus x cubed plus and so forth? That's the power series, the summation n equals 0 to infinity of x to the nth power. And they're saying that in order for the power series to equal that function, you have to restrict x, the absolute value of x, to be less than 1. Or in other words, x is between 1 and negative 1. So the function 1 over 1 minus x does not equal the power series for all values of x. It only equals the power series when when x values are between 1 and negative 1. Okay, so now why do we need that restriction? Why do we need that restriction? What does that power series look like? That's right, Leping. It looks like a geometric series. Okay, well, what's the absolute value? Well, all right, geometric series. What's the common ratio? Well, that's right, Renat. Good. The common ratio is x, and for a geometric series to converge, what is true about the absolute value of the common ratio? Good. It has to be less than 1. So that's what they're saying. That's what they're saying in this Formula 1. Okay, and if you wanted to see how they got that formula, I think it's worth showing. Let me show you here how they get that. Okay, one moment. Okay, so you're welcome to copy this, but you don't have to. I'm just showing it. I'm trying to show why that formula you just saw is true. And remember the formula, the function, hold on, one moment. Got too much stuff here. Got to get too many chords. All right, so by the way, too, when you know, all right, no, that's okay. So our function f of x was equal to 1 over 1 minus x. And so we are taking 1 and we are dividing it by x. And they're saying that when we divide, that's going to equal 1 plus x squared and so forth. How do they get that? All right, well, let's go back to elementary school here when you learned division. Let's say I want to divide 2,475 by 5. So, 5 goes into 24 4 times. 4 times 5 is 20, and then we subtract the 20. We get a remainder of, we bring 47 down, and then 9 goes into, or 5 goes into 47 9 times. 9 times 5 is 45. So we subtract and then bring down the remainder of 25. Okay, and then finally 5 goes into 25 5 times. So 2,475 divided by 5 is 495. So how many remember doing this? I mean, I know you've been kind of using your calculators a little bit, but this is, working division out by hand. How many is this like? How many of you are like, hey, I could do this today if I wanted? That's no problem. All right, Nicole's good with that, and Thomas and Tal and right. All right, good. And Jacob, excellent. So this formula here. This formula for 1 over 1 minus x, where it equals, 1 plus x squared and so forth, we can do the same thing. Take 1 and divide it by 1 minus x. How many remember in pre-calculus when you're doing a division like that with rational functions? How many remember seeing that? Okay, Jacob remembers that. All right, well, let me show you here. So 1 divided by 1 minus x. Okay, so here's the 1. I'm dividing by 1 minus x. 1 minus x goes into 1 time. 1 times 1 minus x is 1 minus x, and then I subtract the 1 minus x. No different than when I did division or take a division, a real number divided by another number. It's no different. Okay, I subtract the 1 minus x, I get a remainder of x, and then 1 minus x, well, the leading term, right, the leading term here is the 1 that I have. Well, the 1 is the term I'm focused on. So x times 1 equals x. So, okay, x times 1 minus x is x minus x squared. Now I subtract that again, just like I do regular division. I get a remainder of x squared. How many times does 1 go into x squared? It goes in x squared times. And then x squared times 1 minus x is x squared minus x cubed. And we keep going. So look at what we're getting. Look at what we're getting here. Look at what we're getting. How many remember doing this kind of thing in pre-calculus? It's something you should have seen. Okay, Nicole remembers that. I've taught pre-calculus, so I know that's taught. Okay, so this is then my answer, right? And so therefore, 1 over 1 minus x is going to equal this series here, this power series, which is a geometric series. It's a geometric series with a common ratio of x. So for values of x, you know, when they say absolute value of x is less than 1, they mean, of course, x is less than 1 and greater than -1, right? So that series would be good for those values of x. Okay, so like for instance, if I, you know, put a little aside here, let's say you had, I want to say this the right way, 1 over 1 minus 0. Okay, 1 over 1 minus 0. If I let me just hold on. So let me have you kind of focus on this formula here. And say you wanted to find 1 over 1 minus 0 using the power series. Well, you don't really need that. You know that equals 1, right? But if we would use the power series, okay, if we would use the power series, we would have 1 plus 1, we'd have, well, let me ask you here, what's x equal to? What's x equal to here in 1 over 1 minus 0? Looking at the formula and 1 over 1 minus 0, what's x equal to? That's right, Renat, it equals 0. That's right. So 1 over 1 minus 0 will equal 1 plus 0 plus 0 squared plus 0 cubed, and so forth. And that equals 1. So all the terms are equal to 0 except the 1 there, and you get 1. So you see the power series works. The power series gives us the answer, the correct answer. And notice x equals 0 falls inside your interval, falls inside that interval of convergence. The interval of convergence is that x is between -1 and 1. Okay. So like for instance, let's say you had something like this. Okay, let me go to the next page here. Let me bring up the whiteboard. Let me just show you here. Okay, so let's say, well, let me just write the master formula down, so to speak, or the key formula. This is the key formula. And the interval of convergence is that x is between -1 and +1. So like for instance, if x were equal to 1/2, then 1 over 1 minus 1/2 would be 1 plus 1/2 plus 1/2 squared plus a half cubed, and so forth. Okay, that would give you, that would equal in the end 2. Okay, that would work because 1/2 falls inside your interval of convergence. Now you might say, well, why, Dr. Duty, would we, 1/1 minus a half? Why would we even use the power series for that? I know that equals 2. Well, I'm just showing you that, hey, if you were to program this power series in a computer, it's going to get like very close to 2. But if you had something like this, let's say you had something like this. Let's say you have, maybe I'll put this in blue. Let's say x were equal to 3. Okay, 1/1 minus 3. What's 1/1 minus 3 equal to, class?
-1/2.
-1/2. That's right, Maria. Well, now let's see if the power series would give us something reasonable. So what are we going to have? We're going to have a 1 plus what's next? So this is the formula here, right? This is the formula. And here are some terms of the power series. So 1/1 minus 3, I'm going to try to use the power series. So, all right, let's write some terms out. I'm going to have 1 plus, what comes next? 3, good, Nicole. Okay, let me see here. Let me put it in blue. What's next? 3 squared, good, Nicole. What's next?
3 cubed.
3 cubed, okay, and it keeps going. Now we know 1/1 minus 3, we know that equals negative, hold on, let's try to make it look good. Okay, we know that equals -1/2. Well, does it look like the power series is going to work here based on what we're seeing here?
No.
No. What's that going to equal, actually, you think?
Infinity.
Infinity. Is this? Well, somebody commented that this is a geometric series. This here, 1 plus 3 plus 3 squared plus 3 cubed, it is a geometric series, Leping. But what's the common ratio equal to? Three, right? And we know that with the geometric series, that won't converge when with a common ratio of 3. But let me ask you, even not even thinking about the common ratio being 3, we 1/1 minus 3 is -1/2, right? It's -1/2, but yet when we tried to use the power series to estimate -1/2, we get infinity. What's going on here? The power series isn't working. Why? Why is that? Why didn't the power series give us something reasonable? Why didn't the power series, why isn't it giving us -1/2? Why when we put x equals 3 in we put x equals 3 in the power series, and it gives us infinity. But we're supposed to get -1/2. But it doesn't work for x equals 3. The power series doesn't work. I can't take this function and evaluate it at x equals 3 using the power series. And that's right, Nicole. It's because it doesn't work because 3 is outside my interval of convergence. The interval of convergence is x is between -1 and 1. So this is no good. No good. I put a big X through that. I can't use this power series to evaluate 1 over 1 minus 3 because that X value of 3 is outside the interval of convergence. Okay, maybe give me a thumbs up if you're comfortable with that. Okay, Thomas is good, and hold on here. Tal and Shazi, excellent. Jacob, Leping. All right, are there any questions? And this is important, you know. This is important because, you know, when you're, you know, later on in life, when you become scientists and engineers and so forth, you don't want to use a power series for except over values of x that are in the interval of convergence. Otherwise, you get chaos. Okay. All right. Very good. Very good. I'll mention one more thing too while I'm at it here regarding the power series, or regarding this function. So this function, this particular section 8.6, we're focused on the function 1 over 1 minus x and writing that as a power series. But, you know, 1 over 1 minus x is very restrictive, right? I mean, 1 divided by 1 minus x is somewhat restrictive. But it's only one function, right? What if I wanted to find a power series for something like 1 over 1 minus x squared? Could I do that? And the answer is yes. Because look here. Here is your power series for 1 over 1 minus x, along with its interval of convergence. Well, let's say you wanted the power series for 1 over 1 minus an apple. Well, so long as the absolute value of the apple is less than 1, then the power series for the function 1 over 1 minus an apple is the sum where n equals 0 to infinity of apple to the nth power. Okay, think about that for a moment. Are there any questions at all on that? All right, give me a thumbs up if you're feeling reasonably comfortable so far with section 8.6. Okay, Nicole and Thomas and Renata and Leping and Jacob. Great. Barak, Gloria, Baraka, Gloria. Wonderful. Does anybody have any questions before we move on? We're going to look at some examples now. And I will point one more thing out, though, before we look at the examples. I want to go back into the ebook. Okay, so again, here is this beautiful, beautiful formula. Okay, for the power series for the function 1 over 1 minus x. And what they do here, they make a note. They make a note of something that like the function 1 over 1 minus x would be the limit of the sequence of partial sums, where the partial sums are the sum of add the terms of the series up to x to the nth power, and that's what they call the nth partial sum. So that's fine. That's fine. So they have a little picture that shows the function 1 over 1 minus x. Okay, that's that function in red. How many remember graphing rational functions in pre-calculus? And the functions kind of look like what you see there. Sure, sure, absolutely. And look what happens here. So so we have, let's see. Now they have the second partial sum. Second partial sum S sub 2 is that black function down there. What does that sort of look like, the second partial sum? What's it resemble? Like a, you know, you've seen, you know, trig for like sines and cosines and, you know, lines and parabolas and cubic functions and all that. What's that S sub 2 function, the second partial sum of this function 1 over 1 minus x? What's it resemble? Well, okay, the cubic, let me just see here. I was thinking, okay, no problem, Nicole. So what's that kind of look like? That second partial sum S sub 2. What's that function look like? What's it resemble? A line, a parabola, a cosine wave, a sine wave? What do you think of those four choices? What is the right? Well, a tangent, Michelle, would be a line, but that S sub 2 second partial sum is not a line, but it looks like a parabola. And that makes sense. That makes sense because if we look at the formula above, we look at that formula above, the second partial sum would just be 1 plus x squared, right? And that's a parabola. Okay, so and you know, again, what they're doing here is they're looking at what are called polynomials based off of the infinite series and studying in the picture how well the polynomials approximate the function. So all the polynomials do very well at what value of x. So look at the red function f, and then look at all these polynomials, so you have a second partial sum, a fifth partial sum, an eighth partial sum, an 11th partial sum. They all estimate the function perfectly at what value of x. Well, let me ask you this. That's right, x equals 0. That's right, Jacob. That's right, Michelle. And as we take more and more terms of the series, so what I'm saying is, if I hold on here. So again, 1 over 1 minus x is 1 plus x squared plus x cubed plus so forth. Okay, so this is our series, and x is between 1 and negative 1. So like S sub 2 is just 1 plus x squared. That's the second partial sum. S sub 3 is 1 plus x cubed. Okay. S sub 4 is 1 plus x plus, wait, hold on. I got that wrong. All right, so S sub 2 is 1 plus, the second partial sum is 1 plus x squared. The third partial sum is 1 plus x squared plus x cubed. Fourth partial sum is 1 plus x squared plus x cubed plus x to the fourth. And let's do one more. The fifth partial sum would be 1 plus x squared plus x cubed plus x to the fourth plus x to the fifth. Okay, so you see those are your first four partial sums there. Are there any questions on those partial sums before I go back to the drawing? All right, well, what I want to focus on is the second partial sum, which is a parabola, and the fifth partial sum, which is what's called a kinetic, it's a kinetic polynomial. All right, and let's go to the picture. Let's go to the picture here. What they've done is, along with the function 1 over 1 minus x, they've graphed, all these partial sums. And look at how the partial sums approximate those partial sums, those functions, approximate the function f. Which does a better job overall? The second partial sum s sub 2 or the fifth partial sum s sub 5? Which does a better job in approximating the function f over a longer range of x values, over a wider range of x values, about 0? Which does a better job? That's right, Nathan. And the fifth partial sum does a better job. Now, it starts to fail, right, as you get closer and closer to 1 and -1. The blue function, that fifth partial sum, starts to fail. Well, and that makes sense because you're starting to go, closer to the, boundaries of the interval of convergence. So the partial sum won't do as well. It's like, I got a great analogy. How many remember the movie The Hunger Games? It might have been the second one. Okay. All right. Remember, okay, Nicole remembers that. Remember in The Hunger Games? I think it might have been the first one. Let's see, maybe it was the second one. But remember when, oh man, I should know her name. Tell me her name, please, the star.
For Lawrence.
Jennifer Lawrence, and Katniss. Thank you, Maria. Katniss is the name in the movie. Remember when Katniss got close to the boundary of the Hunger Games, and she encountered fire and stuff like that? Remember that in the movie? Okay, Nicole. All right, so she was getting outside the interval of convergence, and they didn't like that. So it's kind of the same thing here. These partial sums do great around x equals 0. But as you move away from x equals 0, as you move out and look at x values further and further away from x equals 0, the partial sums start to fail. I mean, in other words, they don't approximate the function well, as you go further and further away from x equals 0. What's the only remedy to? I mean, if you wanted to use a partial sum, and you wanted it to do a better job than these, these partial sums did, like, I guess what partial sum does the best job overall of all of those in approximating the function f? Is it S sub 2, S sub 5, S sub 8, or S sub 11? Which seems to do the best job? Well, okay. We're getting differences of opinions here. Let's see. Let's have a few more responses. So it can be a little tricky question, but so I'm actually glad I'm going over this with you. The S sub 11, the 11th partial sum, is doing overall. That's right, Thomas, and that's right, Leping. It does and thank you everybody for answering. Let's make sure. So the thing is, you see, the 11th partial sum, S sub 11, approximates that red function better over a wider range of x values. The parabola S sub 2, it does good maybe up to, like, if we look from like 0 to a half, the second partial sum approximates our red function well up to maybe x equals a half, but then it starts to be way off. But S sub 11, the 11th partial sum, does a better job. And that would make sense, because to get the 11th partial sum, you have to take more terms of your infinite series. You have to include more terms. I mean, the infinite series perfectly approximates the function, okay? But that is the sum of an infinite number of terms. But if you take more terms of the series and have a partial sum based on more terms of the series, ideally it should do a better job. Okay, does that make sense? All right, Tall's good with that. And how many like the Hunger? I just kind of thought of that, the Hunger Games analogy, because I saw that movie a little while ago. I thought that was a pretty good analogy regarding the interval of convergence. How many are going to kind of remember that? All right, many of you. Good. And you know, that's, hey, you know, that's nothing wrong with that, right? Nothing wrong with that. I think it's helpful to kind of, you know, make analogies. I find it helpful. Okay, great. Well, then let's go ahead and look at some examples here now. Let's go ahead and okay, here's one. All right, let me give you a moment to copy this example down. Okay, so in this problem, we want to find a power series. We want to find a power series and its interval of convergence for this function. The function equals 1 over 1 plus x squared. Okay. So, all right, well, let's take a look at the two results that we have. Just thinking here, so okay, so here is the key result, but we use that key result to get this result that is more applicable, right? And what we're trying to do, right, is we're trying to for this problem, let me focus on this result here. So what we have is 1 over 1 plus x squared, right? Well, can you tell me what the apple is going to be for 1 over 1 plus x squared? What's the apple? Because once I know the apple, I can apply my formula, right? Once I know my apple. That's right, Jacob. It's going to be negative x squared. So we're going to treat 1 divided by 1 plus x squared as just like 1 minus negative x squared. Because then negative x squared, I'll put it, hold on. Yeah, negative x squared is my apple. All right, and so we'll apply the formula. May I go to the next page? Are we good so far? Let me know if you have any questions. Okay. All right, here we go then. So, all right, 1 over 1 plus x squared, I write as 1 over 1 minus a negative x squared. Now, let's remember that 1 over 1 minus an apple, that's equal to this power series. And interval of convergence is that the absolute value of the apple is less than 1. So, well, all right, I use the formula here, right here. And then I also note about the interval of convergence. The interval of convergence is that the absolute value of the apple is less than 1. So for my interval of convergence, I need that the absolute value of negative x squared is less than 1. Well, that means x squared is less than 1, and that means x is between negative 1 and 1. So my interval of convergence for this function is x is between negative 1 and 1. So the power series I get will work for all values of x between negative 1 and 1. Are there any questions up to this point right here? Please let me know. All right, well, for our purposes, you know, and for what you're going to need to be able to do, this power series is not really in a good form. Okay, I mean, we have negative x squared raised to the nth power. It would be good to simplify that. So what I do is I write negative x squared as negative 1 times x squared. That gets raised to the nth power. And that's going to give me then negative 1 to the nth power times x squared to the nth power, right? Because if you have a times b to the nth power, that equals a to the nth times b to the nth. How many remember that rule from their algebra days? Okay, very good. And okay, here it comes. Here, now we're using it again. But even here now, I'm not happy yet. I want to take x squared, and I'm raising it to the nth power, so I multiply the exponents. And so this is going to be my power series. So in other words, my function 1 over 1 plus x squared as a power series is going to equal, if I write out some of the terms of the power series, it's going to be 1 minus x squared plus x to the fourth minus x to the sixth plus x to the eighth minus and so forth. And again, that's for when x is between -1 and 1. Think of the interval of convergence as like a warranty. Okay, it's only good for certain, values, certain things.
Sorry, quick question. Why did you, and you might have said this, I had something else that I needed to do really quickly. Why did you make the 1 plus x squared 1 minus a negative x squared?
Well, I need that so I can apply my formula.
Because
Remember
your
the
formula is 1 over 1 minus x.
1 over 1 minus an apple.
Gotcha. Okay, thank you.
Yes. Okay, good
Thank
question,
you.
Maria. You're welcome. Are there any other good questions? Okay. Well, then let's move on to the next example then. Let me know when you're ready. Are we ready to move on? Okay, tall is good. Maria's good, all right. Jacob's good. All right, all right. I'll be darned, Nicole. All right, well, let's keep moving. Keep going here. Okay. Oh, well, all right. Then here's like a final statement on the problem. I'll let you copy that down. You notice I'm always mentioning the interval of convergence. I'm always mentioning that. Okay. Interval of convergence. Another example I think of, I don't know if you've seen, it's an older movie, but like Raiders of the Lost Ark, the one with the third one. I forget what that's called. The third with oh man, The Last Crusade. That's right. Remember in the end where the knight says you can't take this cup outside this area, and they try to take the cup outside the area, and the area starts falling down, collapsing. Yeah, it's kind of like interval of convergence. Don't go outside. Don't go outside your interval of convergence. Okay. All right. I got some good analogies today. All right. Okay. Let's go ahead and move on here. Let's look at another one. Okay. Here's another function. Here's another function. And as usual, I'll write my formula up here. Don't have to write it in, you have it in your notes, but it's good for the recording to have the formula. There we go. Okay, so here's my function. So this function, we could write it as x cubed times 1 over x plus 2, right? The x cubed in the numerator, we'll deal with that later. Okay, maybe I'll write it like this here. So 1 over x plus 2, how am I going to write 1 over x plus 2? Well, got to be a little careful. Well, here's the thing, though. Here's the thing. Nicole, I almost thought of that myself. But in the formula up here, you have like a constant 1 coming first. Okay? So I'm going to put the 2 first and the x second. Now I still have a 1 here in my formula. I have a 2 here. So the question is, how am I going to deal with that? Well, let me show you how I deal with that. Let's go to the solution. Okay, so x cubed over x plus 2. I write that as x cubed. Well, and let me again. I'm going to just so we can have it in the recording. Let's get the formula down. Apples between 1 and -1, right? Another way of saying that is the absolute value of the apple is less than 1. Okay, so that being said, what I do is I write the x plus 2 in the denominator as 2 plus x. And then I'm going to factor 2 out of the denominator. Why would I factor 2 out?
So that you can end up with your 1.
Very good, Maria. Excellent, excellent. I want to have a 1. Okay, I need to have a 1 right here in order to apply my formula. Okay, and now the 1 plus x over 2, I'll write that as 1 minus negative x over 2. And now I can apply my formula and write this portion of the function as this power series. And right away I say, okay, what's my interval of convergence? When I go from the function to the power series, I like to identify my interval of convergence right away, because it reminds me that the power series only works the function's only equal to its power series for certain values of x in the interval, for values of x in the interval of convergence. So our interval of convergence is the absolute value of a negative x over 2 is less than 1, which means the absolute value of x is less than 2, because you know the negative becomes positive in there. And so the interval of convergence is x is between -2 and 2. By the way, if the interval of convergence, since it's between -2 and 2, what's the radius of convergence going to be? Based on this interval. Well, here's -2, open interval. Here's +2, open interval. What's the distance between -2 and +2? 4. And that's right, Jacob. And so the radius of convergence is half that distance. The radius of convergence is 2. The reason I mention that is because it comes up in WebAssign. They're always asking about the radius of convergence as well. To me, what's most important is the interval of convergence, simply because that gives you the values of x for which your power series is going to work. But nevertheless, Okay, so we are then, here we are. Are we happy with this answer? I mean, is that a nice looking answer? Leping?
Professor, why we don't need to take care of the x x to the power 3?
Well, we do. What we're going to do, we're going to rewrite this answer in a nicer way. And so let's go to the next page and I'll show you. Let's go to the next page. See, Leping, she can't wait. She's so excited, so interested in this material. She wants to see it, this answer look nicer, right, Leping?
Yeah, I saw your handout.
Good, good. All right, well, all right. Here we go. Here's what we had. And what I'm going to do is the negative x, I'm going to write that as -1 times x. So negative x over 2 is like -1 times x over 2 to the nth power. That's just going to give me then -1 to the nth power times x to the nth power over 2 to the nth power. But we still have that x cubed over 2 sitting out in front of the series. The series where n equals 0 to infinity, in terms of the series, what's the series, what's the series like, what's the variable for the index of the series? For the index of the series, what's the variable? What's the index variable? Is it x or n?
N.
N. That's right, Maria. So we can bring x cubed over 3, which is not dependent on n. We can bring that inside the series. How many learned that maybe in a previous class? Where, I mean, we really treat x cubed over 2 like a constant with regards to the series. We just bring it inside the series. That's allowed. And so this gets us to this step, and now we can do a little more simplifying. Okay, x cubed times x to the nth power. We add the exponents, that gets us x to the n plus third power. And then, of course, 2, which is really 2 to the first, right? Times 2 to the nth would give us 2 to the n plus first power. And this is the kind of thing you'll see in WebAssign. Some of these problems, you're going to have multiple choice, like multiple choice. They'll give you like 5 choices with different power series, and you have to pick the right one. Well, sometimes, I mean, usually you have to get the power series in the most simplified form in order to find an answer that matches your answer. And, you know, you want to be careful on the multiple choice, right? You want to be careful on those since you have limited tries. But there we go. We have our answer. There it is. And then what I did below is I just enumerated out some of the terms for you. So I mean, like the first term here, the first term, 1/2 x cubed. That's, you know, -1 to the 0th power times x to the 0 plus 3 power, all divided by 2 to the 0 plus 3, wait, hold on, 2 to the 0 plus 1 power, right? The 1/16 times x to the 6th, that's what? That's the 4th term. That's when n would equal what? N would equal, for 1/16 times x to the 6th, what's n equal to there? That's right, Nathan, 3. So, all right, you know, -1 to the 3rd power, that gets us the negative there, right? Because -1 to the 3rd power is -1. Then x to the 3 plus 3 power, that gets us the 6th power there. All divided by 2 to the 3 plus 1, that's 2 to the 4th, that gets us 16. So, you know. Are there any questions? All right, well, let me know then when you're ready, and we'll move to the next example. And then I think probably we'll take a little break. We have more examples to look at, but let's do one more. And how many of you are thinking, man, I love calculus too, but I'm ready to go on vacation a little bit in, you know, about 20 days. Okay, Tom. Wow, look at that. It's lighting up like a Christmas tree. All the people who, okay, all right. Well, you know, we're not too far away, you know, not too far away. Okay. I understand, Tal. I feel the same. It takes time to prepare for the courses too. But I understand, you know, students, I understand you're working hard, and of course you're feel a little tired. I understand. Okay, let's look at this problem here. let me give you a moment to copy the example down. Okay, so now this is interesting. So, all right, I'll write down that our famous formula again. One over one minus an apple can be written as this power series so long as the absolute value of the apple is less than 1. So this particular function, x divided by 1 plus 4x squared, can I use my formula above directly on this function?
No,
Why not, Maria? You're right. Why not?
because the whole denominator is squared, and if you were to FOIL it, you would have an x term and an x squared term.
That's right. If we were to, I mean, the fact that that power of 2 is there is going to be a problem. And even if you FOILed it, I didn't even think about that, but even if you FOILed it, you're going to have too many terms on the bottom. So we're going to use, what we're going to do is we're going to find a function that we can use, that we can get the power series for using this formula up here. And then we're going to differentiate that function to get this function here. And then we'll differentiate the power series at the same time to get the power series for this function that we're interested in. So let's go to the next page. The function we're going to work with is, it's what you might think it might be. It's going to be, and you can use the zoom feature on the right side to blow that up if you need to. So here again is our solution. I'm going to work with 1 over 1 plus 4x. That's pretty close to 1 plus, that's pretty close to 1. Well, what I mean is, you know, my original function, and just to, you know, ignore that there, my original function is equal to x over 1 plus 4x quantity squared, which I can write as x times 1 over 1 plus 4x, that quantity squared. So looking at this 1 over 1 plus 4x quantity squared, kind of the closest I can come to that is 1 over 1 plus 4x. So I'm going to go ahead and get the power series for that rational function. And I determine that the interval of convergence is negative a fourth and a fourth for that function. Okay. Okay, so let's see here. So we have 1 over 1 plus 4x is equal to this power series, so long as x is between negative a fourth and a fourth. That's based on, this is our result here. All right, so now I'm going to use a little trick here. I'm going to go ahead and differentiate the 1 over 1 plus 4x. And when I differentiate that, I get negative 4 divided by the quantity 1 plus 4x squared. So basically, I can differentiate the function 1 over 1 plus 4x and get a function that is not too dissimilar from the function I'm interested in. Remember, the function I'm interested in is, hold on here, function I'm interested in is this function here. And now I got the square in the bottom. So what I could do, you see, is I could say, okay, well, this negative 4 over the quantity 1 plus 4x squared would be equivalent then to the derivative of the power series that I determined for the function 1 over 1 plus 4x. So you see, that's what I do here. You can ignore this little thing here. So I take the derivative of my power series, but remember, a power series is a sum of terms. And you learned in calculus that when you take the derivative of a sum, that's the sum of the derivatives. And so the derivative of my power series is just the power series where each term is the derivative of the derivative of my power series is equal to the sum of the derivatives of each term of the power series. Now, when I differentiate the negative 1 to the nth, 4 to the times 4 to the nth power times x to the nth power, remember, I'm differentiating with respect to x. So what do I treat negative 1 to the nth power and 4 to the nth power as? If I'm differentiating with respect to x.
Constants.
Those are treated like constants. That's right, Maria. That's right, Renata. And so really, all I'm doing is pulling those constants out front, and I'm taking the derivative then of x to the nth power. By the power rule, derivative of x to the nth power is n times x to the n minus first power. Okay, let me make sure you're good up to here before I continue. Please let me know if you have any questions. Okay, so now notice that that this power series here starts at n equals 0. Hold on. This power series starts at n equals 0. And I'm saying, oh, it equals the same power series starting at n equals 1. Now, how can that be? Well, let's take a look. We'll go to the whiteboard. And then there's another statement too here, the last statement. But let's go to the whiteboard, and let's talk about it. Okay, so here's that power series. By the way, can I bring any of these 4 terms out in front of the series? Can I bring them out, factor them out?
No, they all have n in them.
Excellent, Maria. They all have n in them. All right, so let's see here. Let's write down the first term of the series. The series starts at n equals 0. Okay, so I can write the first term as -1 to the 0th power plus 4 to the 0th power. I'm sorry, times, hold on, that's a times, should be a times. One moment. Okay. Times 0, and then x to the 0 minus 1. And then the rest of the series, starting at n equals 1. I can just put that there. What's this term equal to, the first term of the series? That's right, Nathan, 0. And therefore, because of the 0 here, right? Doesn't matter what those other terms are, they're being multiplied by 0. So this is why the series starting at n equals 0 is the same then as the series starting at n equals 1. We generally, with series, power series, we don't want to have like nonsense terms. We want terms that have meaning. Well, 0 doesn't have any meaning really, right? So we can throw that out and start the series at the index n equals 1. Are there any questions on that? All right, well, now let's say that you wanted to rewrite this power series, and so now we're we're focused right here. This is our new power series. This is our new power series here, right? We're not looking back. That's our new power series, and I want to rewrite that power series with a different starting index, maybe n equals 0. Well, in order to do that, I have to adjust the ends, right? I have to adjust the ends. So you see that if I start at n equals 0, the -1 to the nth power how would I adjust that if I change the index to n equals 0?
You
How
have to add
about,
one.
that's right, you have to add one. Right? You have to add one. Same with the 4, you have to add one. Same with the n. You have to add one. Let's try to make that look a little better. Hold on. Hold on. Just give me a moment here. All right, hang on here. So, right, you have to add one. Doing the best I can here. And what about x? What power would x be to? So up here, the power x was to the power n minus 1. That's right, Nathan. Now it becomes x to the nth power. You see that? You see how that works? Why that works? Please let me know if you have any questions. Both power series, starting at n equals 1 and n equals 0, both of them generate the same terms. But sometimes scientists like power series to start, like, for instance, at n equals 0. They just sometimes do. And this is something else you have to be careful of in WebAssign. You could have a problem where you find a power series for a function, and it'll give you answers with, like, some will start at index n equals 1, some will start at index n equals 0, and, you know, only one of them's right. Or, you know, I think for the way it is, they have just like one right answer. So you have to be very careful before you know, select your answer, right? You have to be very careful. And certainly for the final exam too, because, well, you always have to be careful with the multiple choice question. Okay, so let's go back then, back to the, we're not done yet with the problem. Okay, hang on here. No, I don't want that one. Let's see. No, it's the next one over. Hold on. Right, so this is the one we're working on. And we differentiated the function 1 over 1 plus 4x, and now we're down to here. So -4 over the quantity 1 plus 4x squared equals this power series. So now let's see, but remember the function that we're interested in, again, the function that we're interested in is going to be x divided by 1 plus 4x quantity squared. Well, you've handled the squared part. I mean, you've got a series that only differs by well, you got a -4 on top here. You have an x on top here. So we can resolve that. So on the next page, what I do is I write the x over 1 plus 4x squared. I write that function as -4 over the 1 plus 4x squared times x negative x over 4. So my goal is to bring in the -4 divided by the 1 plus 4x squared, because I have a power series. I have a power series for that, right? Right? I have a power series for that, namely this power series. Now the negative x over 4, it doesn't depend on n, so I can bring that inside the power series. And now basically it's just a matter of doing some manipulation. Let's see here. Let me just so I'm trying to put in a lot of detail for you. If you take differential equations, you'll be seeing this kind of thing as well. We can solve differential equations using power series solutions. So this is very important. So what I do is the -1 to the n plus first power. That's like -1 to the nth times -1 to the first. And then the negative x over 4 is -1 to the first times x over 4 to the first power. So what I get then is -1 to the n plus 2 power, because I add my exponents for the negative ones, which is 1 plus n plus 1. And then, incidentally, the 4 to the first power and the 4 to the n plus first power, I subtract the exponents. 4 to the n plus first over 4 to the nth is 4 to the n plus first minus n. Wait, hold on. I have something wrong there. Hold on. I don't want an n up. I want a 1 here on the bottom. Absolutely fascinating stuff, for sure. So I get 4 to the n plus 1 minus 1 power. That's 4 to the nth power, and that's how I get this. Okay? And now the -1 to the n plus 2 power, okay, please let me know if you have any questions. The -1 to the n plus 2 power, I write that as -1 to the nth power. Why would that be true? Well, -1 to the n plus 2 power is equal to -1 to the nth power times -1 to the second power. But what's -1 to the second power equal to? Come on, you know.
Sorry, what was your question? I was taking notes.
Okay. What's -1 to the second power?
1.
1. So hence you get -1 to the nth power. Very good. So again, with remote teaching, I could, like, for instance, I could let you all copy it down and then talk about it, but I think some students, how many find it helpful that I'm just sort of, I'm commenting on it like I were writing it down on the board, step by step. Is that, is it helpful that I comment as I go along? I guess maybe it depends. All right, so for some of you it is, fair number of you it is. Okay, good. All right, good. Well, we're done. That's our power series. So then the function x over 1 plus 4x quantity squared is equal to that power series, and it works, of course, it'll work when x is between -1/4 and +1/4. This is really quite amazing, right? You're taking functions, and rational functions tend to be regarded as complicated functions, That's why, for instance, how many remember, like, graph the rational function? How many remember, like, vertical asymptotes and horizontal asymptotes and oblique asymptotes? How many remember those kind of things? Yeah, Sean remembers that. And so the fact that we can take a rational function and represent it as a power series over an interval of convergence, of course, is really a fascinating idea. How many think this is kind of fascinating, what you're learning in section 8.6? Like, all right, a lot of people, Maria, Jacob, Tal, and yeah, this is, this is really, really important stuff. All right, are there any questions before I stop the recording? All right, so what I'll do, we're going to continue on with some more examples from section 8.6, but I'd like to give you a chance to work a little bit on some exercises from section 8.6 now. And then, the earlier ones are kind of like the ones we did here. So, I want to be, well, I'm just going to let you work a little bit. Actually, what I'll do is I'll open up section 8.5 and 8.6. Okay, so let me stop the recording.